Section 1 Introduction. We're going to delve into the world of large language models, LLMs, and how they're being used in the field of machine learning. These models have shown significant improvements in performance, but fine-tuning them can be a time-consuming and resource-intensive process. A popular alternative is to use in-context learning, ICL, where the model learns to perform a task based on the task's definition and a few examples. This method has proven to be effective and allows for quick experimentation without the need for model training. However, as ICL becomes more widely used, it's become clear that LLMs are sensitive to the prompts they're given. This makes the process of creating prompts for different tasks, known as prompt engineering, a challenging and time-consuming task. But it doesn't have to be a guessing game. We can use data to guide our choices. For instance, choosing examples that are similar to a new input has proven to be more effective than choosing examples at random. This approach is based on the idea of using information from similar situations to solve a new problem. But there's more to it than just choosing the right examples. We also need to consider how useful each example is to the LLM's existing knowledge and what clues about a test input can be derived from that knowledge. These questions can only be answered by interacting with the LLM itself. For instance, in a sentiment classification task, we noticed that one model often confused the labels very negative and negative. This observation led us to investigate whether we could use the model's existing knowledge to select more effective examples. Our approach involves using signals from the LLM about the output label space of both the new test example and the training data. We believe that understanding the model's confusion about the new test example's output label can help us choose examples that reduce this confusion. To do this, we propose considering not only the ground truth labels paired with these examples but also their model prediction. We build our methods on the idea of semantic similarity, which has proven to be the most effective across sentence classification tasks. We start by using a retriever to find examples with similar input text. Then, we identify the two output labels that the model is most confused about and select the top-ranked examples whose ground truth label falls within this set. We also look for examples that the model has misclassified, as showing the model a previously misclassified example could help it correct its mistake. Finally, we add a constraint to select only those examples whose model prediction falls within the ambiguous label set. To test our approach, we conducted experiments on 3 text classification tasks that have fine-grained nuances in the label space. Our results showed that adding constraints, such as considering label ambiguity and limiting ICL examples to misclassified examples, led to improvements in F1 macro scores. We also found that our methods were more effective on a smaller model. We believe this success is due to the ambiguous label set acting as a good proxy for the gold test label, guiding the model to make the correct prediction. Section Summary. In this section, the authors discuss the challenges of prompt engineering for large language models, LLMs, and propose a method to leverage the model's existing knowledge to select more effective demonstrations for in-context learning, ICL. They derive signals from the LLM about the output label space of both the new test example and the training data to reduce the model's confusion. Experimental results show that adding label-based constraints leads to significant improvements in F1 macro scores, especially on smaller models. The authors attribute this success to the fact that the ambiguous label set acts as a good proxy to the gold test label and guides the model to make correct predictions. Section 2 Proposed Method. In our proposed method, we typically start with a set of training data, which we'll call D_train. This dataset includes pairs of inputs and outputs, represented as x_0, y_0, through x_t, y_t. Our goal is to choose a subset of these pairs, which we'll call demonstrations, to use as prompts. Our method for selecting demonstrations involves 3 steps. First, we find examples from D_train that are semantically similar to each test example. Second, we identify what we call the ambiguous label set. Finally, we look at the model's predictions for D_train to find examples where it made mistakes. Let's go into more detail on each step. In the first step, we select demonstrations for each test example by finding examples from D_train that are similar in meaning to the test input. The idea is that seeing similar examples will give the model a hint about how to handle the new input. To do this, we use a tool called a retriever, which ranks examples from D_train based on how similar their text inputs are to the test example. We then select the top k input-output pairs from the ranked D_train to use as demonstrations. In the second step, we construct a prompt for the test example and use the model's log likelihood to score each possible output label given the prompt. We then identify the two labels with the highest scores, which we call the ambiguous label set, for the test example. In the third step, we look at the model's predictions for the training data to find examples where it made mistakes. These are what we call hard demonstrations. We believe that showing the model these examples, along with their correct labels, will help it correct its own mistakes. We also make sure that the model's prediction for these misclassified examples is one of the labels in the ambiguous label set identified in the second step. We tested our method using the Flan Palm 2 model, which is a model that has been fine-tuned on a variety of data types, including web documents, books, code, mathematics, and conversational data. We found that our method of selecting demonstrations worked better with this model than with general large language models. We also used an off-the-shelf retriever that was fine-tuned on Mount 5 base using an unsupervised objective. We found that the order in which the demonstrations were presented could affect the model's performance, so we randomly shuffled the order of the demonstrations and reported the average results. Finally, we tested our method on 3 text classification datasets that met certain criteria. The output label space needed to show fine-grained nuance that spanned multiple labels, and the datasets could not be part of the Flan mixture to avoid any inherent bias from the underlying model. Section Summary. In our proposed method, we follow a 3-step approach to select demonstrations for the ICL regimen. First, we extract semantically similar examples from the training data to provide hints to the model. Then, we identify the ambiguous label set for each test example and construct a prompt to help the model resolve the ambiguity. Finally, we extract misclassified examples from the training data, focusing on those that fall on the decision boundary between the ambiguous labels, to guide the model towards the correct label. Section EDOS, Task B. We're going to delve into the specifics of several tasks and methods used in our research. Firstly, we have Task B of the Explainable Detection of Online Sexism, EDOS. This task involves classifying sexist content into 4 categories. 1. Threats, plans to harm and incitement. 2. Derogation. 3. Animosity. And 4. Prejudice discussion. Next, we have the Stanford Sentiment Treebank, SST. This is a sentiment classification task that uses movie reviews and classifies them into 5 categories: very negative, negative, neutral, positive, and very positive. We also use the Go Emotions dataset, which is a sentiment classification task that includes a neutral category and 27 emotional classes, such as admiration and fear. These are collected from Reddit comments. Given the large number of labels and the limited sequence length, it's crucial to choose a concise yet effective prompt. In our experiments, we excluded about 24,848 examples that had multiple labels for a single input to simplify the setting. We used several baseline methods for comparison. The first is the frequent label method, where we simply choose the most common label as the prediction for all test examples. The second is the zero-shot ICL method. Here, we add the task definition to each test input and prompt the models. We then use the model's log likelihood to score each output label given the prompt, and choose the label with the highest score. The third is the static n-shot ICL method. In this method, we manually select n demonstrations from the training data, 1 for each of the n output labels. These demonstrations are static for all test examples. We then combine the task definition, n demonstrations, and test example as the prompt for ICL and use the log likelihood scores to get the model prediction. The fourth is the retriever-based ICL method. Unlike the previous method, here we retrieve demonstrations for each test input. We use a retriever to find the k nearest neighbors from the training data. We then select 4 or 8 of these examples as ICL demonstrations. Finally, we have our proposed method, Ambiguity-Aware. This method considers both semantic similarity and label ambiguity when selecting demonstrations. For each test example, we first retrieve the top k most similar examples from the training data. At the same time, we also identify the two labels that the model is most confused about. We then select those examples as demonstrations where the ground truth lies in these two labels and they are misclassified. The model predictions on these examples are obtained from the zero model. Section Summary. The Task B of Explainable Detection of Online Sexism involves classifying sexist content into 4 categories: threats and incitement, derogation, animosity, and prejudice discussion. The baselines for this task include selecting the most frequent label, using zero-shot and static n-shot demonstrations, and using a retriever to retrieve nearest neighbors for each test input. The proposed method, Ambiguity-Aware, considers both semantic similarity and label ambiguity to select demonstrations for each test example. Section plus gold+mis+pred. We're going to select certain examples from the set R, X_T, as demonstrations. These examples are ones that have been incorrectly classified, but with a twist. The ground truth of these examples falls within a set we'll call L_ambig_T, and the model's predictions for these examples also fall within this set. We then use these selected examples to train our model from scratch. We've experimented with different versions of our model, and for each version, we've chosen either 4 or 8 demonstrations to use for training. We've evaluated our models using a measure called the F1 macro score, which is a good way to compare performance when dealing with unbalanced datasets. We've also looked at accuracy, precision, and recall. Our findings show that our proposed methods outperform the baseline methods. Even our zero-shot model, which only uses a task definition and no demonstrations, performs well. However, we've found that adding just a few demonstrations can boost performance even further. Interestingly, our larger model, FLAN-POM2L, benefits more from the addition of demonstrations than our smaller model, FLAN-POM2M. This suggests that larger models are better at learning from context. We've also found that for 2 of our tasks, SST and Go emotions, the larger model performs better with 4 demonstrations than with 8. This suggests that more isn't always better when it comes to demonstrations. We've also found that considering the output label space is as important as considering the input similarity. In fact, our methods that consider the output label space outperform those that only consider the input similarity. We've also found that considering misclassified demonstrations that fall on the decision boundary of the test example can lead to the best performance. We've also noticed that as we introduce more constraints, we have to sacrifice semantic similarity to the test input. For example, in one of our experiments, we had to select up to the top 16 retrieved examples to get 4 demonstrations that satisfied our constraints. For another constraint, we had to go up to the top 55, and for yet another, we had to go up to the top 250. While previous studies have suggested that greater semantic similarity can enhance model performance, our results show that our methods can still outperform those that prioritize semantic similarity. Section Summary. In this section, the authors propose a method called Ambiguity-Aware for selecting demonstrations in few-shot learning tasks. They find that their proposed methods outperform baselines and that larger models benefit more from the addition of demonstrations. They also observe that considering output label space is as important as considering input similarity when selecting demonstrations. Additionally, they explain that as they introduce more constraints, they need to sacrifice semantic similarity to the test input, but their methods still outperform retriever-based baselines that prioritize semantic similarity. Section. The ambiguous label set is a good proxy for the test gold label. We've discovered that a set of ambiguous labels can serve as a reliable stand-in for the actual test labels. While we've found that using pseudo-demonstrations, which are demonstrations with random labels instead of the actual ones, doesn't impact the final performance, we've also noticed that pseudo-demonstrations can negatively affect performance when they're similar to the test input, like those from a retriever. We call this the copying effect hypothesis, which suggests that the model's predictions are influenced by the labels associated with the inputs in the demonstrations, especially when these inputs resemble the test inputs. This implies that the best performance could be achieved if the labels associated with the inputs match the actual label of the test example. However, since we don't know the actual label of the test example beforehand, the challenge is to find a way to approximate this label. We've found that our ambiguous label set serves as a good approximation. In our research, we calculated how often the label paired with ICL demonstrations matched the actual label of the test example. We discovered that, on average, 44.2% of the demonstrations from our proposed methods, using ambiguous labels, had the same actual label as the test example, compared to 30.9% from the reader method. This is why incorporating the ambiguous label set into the demonstration selection process results in better performance. This analysis also provides insight into the effectiveness of retriever-based ICL. We found that demonstrations chosen solely based on input text similarity were only 13.3 percentage points, on average, less effective than our proposed methods. This confirms that finding demonstrations similar to the input text also leads to selecting demonstrations that are likely to have the correct label.